Welcome to KBOCC Earth Science. This is Chapter 8, Geologic Time. In this presentation, I'll be covering the following topics: thinking about time, the history of relative time, geologic time, numerical time, and rates of change. So, time. What is it? How does it relate to geology? Well, let's take an example of this picture here. How long do you think the landscape has looked like this? How far back should you go in time to notice something different? Will people see this if they hike here in 80 years? Evidence for events in Earth's past are recorded in the rock record. What that means is if something major happened, you can usually tell when and what it was by looking at the geology that was present at the time. A good example of this would be asteroid impacts. Geologists assign ages to these events on the geologic time scale. The geologic time scale is very different from the you and me everyday time scale. We don't talk months and years in geology. We talk millions to billions of years. Here we have examples. On the right hand, we have eras, the Cenozoic, which is our current era. And then you go back about 65 million years, you hit the Mesozoic. Go back about 250 million years, you hit the Paleozoic. And that little section there, those three eras covering basically all creatures on this planet, falls in the top bracket of the Earth's aeons. Those three eras, Cenozoic, Mesozoic, and Paleozoic, are all part of the Phanerozoic eon, which is the last 542 million years, the last 500 million years on this planet. And that is about a quarter the size of the previous eon, which we call the Proterozoic. Proterozoic meaning when the protus, or the first life, essentially started to form and become relevant to the planet. And that is only about half the age compared to the Archean, which is kind of before life as we know it originated. A lot of the Archean kind of doesn't have life in it, as shown by this example here. Of course, it's important to talk about the paradigm shift that goes along with this understanding of just how old the Earth is. In the 17th century, science was young and geology really wasn't a discipline anymore. So if you look at today, as we talked about in Chapter 1, you have hypothesis testing as a method of supporting ages. Back in the 1700s and prior, you kind of went off of religious text as a way to understand how old something was. Structures such as the oldest Egyptian pyramids and the Great Wall of China fall within a historical timeline that humans can relate to. But it is important to remember that human timeline is a sliver of a sliver of a sliver of the Cenozoic. So we are talking about vastly different numbers when we talk about geologic timescale. The picture you're looking at here, each of those lines that you see as you look at these rock records here, that describes literally millions and millions of years of geologic activity, far surpassing anything related to human achievement, far surpassing humans as a species themselves. So let's discuss relative time. Which came first, which came second? That is how we define relative time. Not an exact age, but my older brother or my younger sister. That is an age relative to you. A good way to understand relative time is to look at a rock layer and realize the things in the bottom are older, because what happens? How does geology form? How do rocks form? They build up on top of themselves. So if I look at this picture here, it's a fair assumption to say that the stuff at the bottom of the canyon is older than the stuff at the top of the canyon, because sand and sediments and everything, as we'll talk about in later chapters, slowly accumulate. This is in geology referred to as superposition, or stuff that's in the bottom is old. In this example, A is older than B, which is older than C. Another interesting thing we can take from relative time in geology is what's known as cross-cutting relationships. As you see here, A, B, and C are all overlain by D, but A, B, and C are at an angle. They're bent, they're tilted, right? So how can you relate the ages of A, B, and C to D? Well, if we take that tilt, step it back, we can look at superposition, say that A is oldest, then B is oldest, and C is oldest. And based on the way that geology forms, we can say that D is the youngest because D is on top of all that and cuts across everything. So at some point, A, B, and C were formed, tilted. Again, we'll get more into all these concepts as we go. And then D was deposited on top of it. Relative time, older, younger. So when you look at examples like this, you can take A through G, large amount of information here, and you can figure out the relative ages of things. For example, here, we see that a fault cuts all layers except for G, that red line there. So what is older, the fault line or G? Well, we would say G is older because if the fault line was younger than G, you would expect the fault line to go through G, right? So the rock was faulted, earthquake, for example, and then G arose. Same here, we have F and G cut across the top of E, right? You see that in the corner here? So what does that mean? Well, in order for E to have its top cut off, E had to exist in the first place. So therefore, F and G are younger than E is. And lastly, we notice along the same lines that E cuts straight through A, B, C, and D. Therefore, we can assume E is younger than A, B, and C, and D because it couldn't cut through them if they didn't already exist prior. So we look at more complicated rocks, such as this here, we can take a moment, do some science, gather information, and extract out something relevant and useful from it to understand the history of what we're looking at here. There's a lot of excitement going on in this picture. I hope when taking this class, you can learn to appreciate that excitement and maybe, tell your friends. There is deposition, erosion, tilting, a whole bunch going on in this image here. In the 18th century, James Hutton watched the landscapes of his farmland and invented a modern concept of geologic time. He observed that the landscape remained unchanged in his short human timescale. Therefore, if during his time, things didn't really change, but we have such variety in the world, geology must be a slow-acting process. Things take a while to happen in a geologic sense. We call that concept uniformitarianism. The present is the key of the past. If you're watching something happen today, it's fair to assume that same process happened in a very similar manner at a different point in time. Rivers flow down hills now, rivers flowed down hills in the past, that sort of thing. All land should be worn flat unless some process renews it, right? So if the river is flowing, and that river's been flowing for a while, it's picking up sediment for a while, how does it keep doing this? Well, we must have some formation, some ability to create new land for that erosion to take place. Hutton here, James Hutton, thought mountain building could be an example of this. Now, this was a very controversial thing at the time because religious texts didn't really talk about this process. So it was going against the norm at the time. Here we can see an example of the crosscut of the Grand Canyon. So at the very top of the Khabib Formation, going all the way down to Zoroaster granites. And even below that, of course, the Grand Canyon supergroup. Everything here is a unique geologic layer that has its own story to tell and its own, story to tell. I can't think of a way to phrase that. The rocks at the bottom are older than the rocks at the top. The Tapete sandstone is older than the red wall limestone there in the center. Why? Because the Tapete sandstone is lower. If you look at the lower units, which is older, the granite or the schist? Well, we have the Vishnu schist, which is this orange stuff, and then we have the Zoroaster granite, which is the blue stuff. It looks like the blue stuff kind of wiggles its way through the schist, right? Well, in order for the Zoroaster granite to wiggle its way through the schist had to be there first for the granite to wiggle, right? That is how we can build these stories. That's how we can explain what's going on. And when I discuss what a schist is and a granite is, in later chapters, you'll see how all that plays together. And then, of course, when we get to schist, you understand it's a metamorphic rock, which then expands on the concept even further. And here we have a geologic history of the Grand Canyon based on the rocks that we're looking at, based on the variety in here. And it goes left 1, 2, 3, 4, and then right 5, 6, 7, 8. It's a bit confusing. I don't know why I just didn't read like a book, but whatever. I think it's worth noting the Grand Canyon is very heavily studied because it's such a beautiful job of explaining this process. And as you learn more, if you have a chance to go to the Grand Canyon, look out for this stuff. It is very cool. Here we have sedimentary rocks on the top, igneous metamorphic rocks on the bottom. Why is that? The sedimentary environment's involved. So when you look at here, you see volcanic rocks in the bottom and sedimentary rocks in the top, again, building these stories, figuring out this process. What built the Grand Canyon? Why are the igneous rocks and metamorphic rocks in the bottom? And then, of course, an unconformity. We'll get to that as we go further along. Lots and lots of interesting stuff. So hopefully you can kind of figure out this relative time scale, right? Because in real geology, it's much more complicated than what we're looking at here. You can have overturned faults. You can have lots and lots of variety. And doing proper science, like we talked about in chapter 1, will allow you to unfurl the story and really take a deep dive into what you're going at. So let's talk index fossils. Index fossils are fossils of organisms that lived at a specific time and only at a specific time. So if you find that fossil in a rock layer, you know how the rock layer is based on the fact that the fossil exists there. Something like a chicken. Chickens haven't existed all throughout time. So if you find chicken bones in the ground, you know it's relatively young rock. A trilobite doesn't exist nowadays. So if you find trilobite fossils, you know it's older than modern rocks. Example shown here. Which of the fossils in the diagram would be the best index fossil? Well, you need a fossil that only exists in certain layers and is kind of easily shows what is going on. So if we look at these examples, fossil 1 exists in shale A, it exists in shale B, and it exists in shale A and shale B, but it's top and bottom, it's kind of going everywhere, right? Whereas an example such as fossil 2 only exists in limestone B. And fossil 3 is kind of everywhere. So we know fossil 2 exists in limestone B. Therefore, fossil 2 is a fantastic index fossil because we know exactly how old that is because that fossil does not spread around its age everywhere, such as fossil 1, which exists at the top and the bottom of the north column on the left there. So it's a huge time frame that fossil 1 exists. And fossil 3 is, well, just bonkers everywhere, right? Funny enough, the relative dating that we talked about before correlates very well with the index dating that we talked about just now. And Grand Canyon is a good example of this. Here's pictures of trilobites that we talked about before. Trilobites only exist at a certain time frame. So if you find trilobite fossils like these beautiful examples here, you can detail and you can pin down a time at which the rock was formed. Certain shapes of mollusk shells follow the same philosophy. And these wonderful creatures here, all of these examples exist and only at a certain point in time because, as shown here, there's consistency with certain fossils. Therefore, we can pin down the times when they existed. Again, just wonderful looking fossils, right? And these things are found at the Grand Canyon. Here's some tracks. That's really cool, right? Fossil mud tracks. Although they do not preserve the bioorganism, trace fossils like that tell us a lot about what's going on. And again, something I want to stress here, the fossils that we're looking at, these trilobites exist in the rocks that are the age of trilobites. They don't exist at the rocks that are younger than trilobites. So when you hit trilobites, you know that you're in an older rock than something else. This coral, for example, let's say this is a younger fossil. You only find it at the top of the fossil record. That's why we use it as an index fossil. So let's take a look at this ancient reef here and predict which rock unit in the Grand Canyon is most likely to have formed given a depositional environment like this. So, as I said before, we have the Proterozoic with the early life, the Phanerozoic, which is the most of life. And before the Phanerozoic, we really don't have fossils because Proterozoic, early life, we're talking microorganisms, singular multicelled organisms at that point. Archean is kind of nothing. And then all of big life, all of this size life, more or less exists in that top little pink section, the Phanerozoic. Cool. As said before in chapter 1, when I get to these questions, I'm not going to go over and answer them. Instead, I'm going to take a couple moments, say this is a question. If you want to pause and answer the question, move on. That's up to you. Continuing on. If you would like to pause, go right ahead. Cool. So another interesting thing about fossils is their connection with extinction. You're all probably aware of the extinction event of the dinosaurs, right? Asteroid came down, killed everything. We don't have dinosaurs anymore for a very specific reason, right? Did you know, in fact, there was more than just the dinosaur extinction as time went on? Here, this chart shows the purple part there is the amount of species or genre on the planet. And then those blue arrows coincide with places where the species numbers dropped dramatically. So the most right-hand one under that big dip right there, that's the dinosaur extinction, Jurassic, Cretaceous, right? But before that, we had lots and lots of stuff happening, lots and lots of creatures appearing and then dying off in mass. How do we know that? Well, because the creatures that appear in here, the Ordovician, these fossils don't exist afterwards. They died off dramatically. Fossils found in rocks deposited before mass extinction are substantially different from those found after the extinction. Again, this is the thing I'm going at here. Before and after each of those blue arrows is very distinctive fossils. You don't find the fossils of the same animals before and afterwards unless they survive the extinction. Sharks should be an example of that, of course. Sharks existed with the dinosaurs. Sharks exist today. We have shark fossils throughout this right hand of the graph here. So, as I said before, the first one we talked about was the KT extinction event, the Cretaceous-Tertiary extinction event around 65 million years ago. The one that killed off the dinosaurs, thought to be a comet, still an area of intense and thorough interest. But as I said before, we have ones before that. It's just the Permian-Triassic extinction event about 250 million years ago. Permian-Triassic, this area right here, that's a huge dip. You're losing, what, over 60%, 70% of all known species at that point? Exactly. 98% marine and 70% land species. And we don't really know why everything died about 250 million years ago. We have a good example of why everything died 65 million years ago, but we don't really know for 250. So why do we say this? Why is this an important area of conversation? Well, knowing why something died could be useful for us. If an asteroid hits the planet, we know asteroids wipe out life. That's something important to study. And then, of course, how things respond to that. Mammals arose due to the dinosaurs dying, in part for many reasons. Mammals are warm-blooded and can survive colder temperatures better, right? Geologic time checkpoint. Again, it's in the spot where I'll pause. If you'd like to go at it, have a go at it. It's up to you. Another concept survey. Feel free to pause here and answer the question if you want. All right. Let's get into one of the last sections of this chapter, numerical time. Early methods for determining the age of the Earth are flawed and yielded very different results. Before the depth of science and the ability of technology and communication enhanced far enough that we could study the world uniformly, scientists tried to figure out how old the Earth was. One way was maybe salinity of the oceans. We know that salt is delivered to the oceans from the continents via streams. So if you look at the mass of salt in the oceans and dial it back, we should be able to figure out how old the Earth is. Well, that kind of makes sense, but we eventually realize that formation of chemical sedimentary rocks exists in the ocean, which takes the salt out of the ocean, turns into a rock. Suddenly you don't have a very simple system to work off of, and salinity of the oceans is not useful. You can also maybe look at how long it takes a rock to cool. The Earth was molten hot at one point, and now it's obviously not. How long it's taken a rock to cool? Maybe that's how old the Earth was. Well, but there's other sources of heat beyond just the creation of the Earth. Can't really use that either. What about isotopes? Unstable isotopes have the key to the numerical age of the Earth because certain radioactive elements, uranium, plutonium, you know these words here. Here we have examples of potassium, decompose at a set known rate. So if we watch these radioactive isotopes, these radioactive atoms decompose, we can tell how long they've been decomposing and then dial it back to tell you how old the rock was when it was formed, because it formed with fresh atoms and then decomposed over time. Here's an example of uranium turning into Neptunium, which is turning therefore into plutonium. This is going into chemistry and physics that this class won't really cover, but I'm going to touch on this topic here because it's a very good way to figure out exact ages for things. You know, back here, there we go. I had all these ages at the bottom there. There's a reason why I can put distinct ages and not just old or younger. One of the examples, as I said, is this radioactive decay concept. So, okay. If you take an electron, such as from this potassium 40 here, and you take it away from, actually, let me read this. What am I doing here? Okay. The addition of an electron neutralizes positive charges of one proton, changing it into a neutron. And the loss of an electron gives one neutron a positive charge, changing it to a proton. So this is a conversation about isotopes and how you can alter a atom and alter its properties to make it more or less stable, because atoms like to be stable, right? They like to be neutrally balanced, have equal numbers of electrons and protons. When they don't, they energize and they want to do stuff. And that energized state causes the decay that we're talking about. And this is super simple terms. Again, this is not a chemistry class or a physics class to go over this stuff. But this disturbance, if you will, with the atoms causes them to decay and, as shown here, change. And when they change, in this example here, you're gaining protons as you go down 92, 93, 94, the mass number, right? No, not mass number, the atomic number. There we go. As you change the element, you can record that change. And if we know how fast something changes, and let's say this process takes X number of years to go from uranium-238 to plutonium-239, if this takes 100 million years and we know about 75 million years along, it's neptunium, the NP in the center there, and I find a rock that's a chunk of NP-239 in it, I know how old it is because it took 75 million years to turn from its initial rock, U-238, into that. And I know in another 25 million years, it's going to be plutonium-239 there at the bottom. Super, super simple glossing over of radiometric decay. Feel free to read the book for a more in-depth understanding, or find a good YouTuber or something like that. Again, I'm not going to focus too deep on the chemistry and physics behind this for the class. Half-lives. This is exactly actually what I was talking about. So a half-life is the process that we're talking about here, but I can use it for a singular example as shown here. when you start a radioactive decay, when an atom starts to radioactively decay, it exists as 100% of what's known as parent product. All the atoms in the rock that are going to decay start out as they're in their initial state. Over time, they turn into the other thing. Again, here, the uranium-238 turns into uranium-239, which turns into Neptunium-239, which turns into plutonium-239, right? This is the decay path, if you will. And over time, we can chart how far that goes. And a half-life is how long it takes for half of the parent product to turn into something else. See that 50 right there at the center for one half-life? So if I look at a rock and I see that it's 87.5% daughter product, I know it's went through 3 half-lives. And if I know how long a half-life is, therefore I know how old the rock is. I'm sorry I just explained things twice. Again, this is a very complicated subject. I suggest if you'd like to learn more, read the book a bit more thoroughly, or Google radioactive decay and watch a YouTube video of a respectable YouTuber, someone, like someone with a PhD, essentially. If you'd like to learn more, or just ask me, shoot me an email. I can send you some fantastic sources. Another checkpoint. Again, feel free to pause the video if you'd like to cover this. Again, another checkpoint. When I give you homework, it's going to be questions similar to this. So if you want to have a go at it now, as usual, feel free to leave the comments in the video. I can respond answering the questions, or shoot me an email, whatever works best for you. Cool. So this is the thing I was getting at, where as science developed, we were able to better correlate different the geology of the world and saw all these connections go back and forth. Here we have blue Cambrian rock, yellow, I'm going to say, Precambrian rock, and red igneous rock. That red igneous rock is something that we can radiometrically date, as I said before. So when we radiometrically date this igneous rock all throughout the world, we, funny enough, find that a lot of it is very similar aged. The volcanic ash in Australia is 526 million years old. The granite porphyry in England is 560 million years old. And the rhyolitic lava flows in Canada is 551 million years old. So that igneous rock layer that we find all over the world is dated the same age, meaning all that igneous rock was produced relatively recently to each other in geologic time. So all those layers are the same age. The surrounding layers, Cambrian, Precambrian, the igneous rock goes straight through it because in those individual environments, the geology was happening at different speeds, essentially. So we can combine all these rock layers together to form a geologic column, if you will, of exactly how old things are based on that. So let's talk about rates of change, go a bit more in uniformitarianism. So James Hutton suggested that features on the Earth's surface were formed in the same slow process that we see today. Everything you see that's happening now to form geology was happening at that same speed XYZ million billion years ago. So we have the Green River in Canyonlands, this nice swooping river here. The process that's cutting into the rock, that river, has been doing that same thing over time. Ancient mud cracks form the same way that modern mud cracks form. You can find rocks that have mud cracks in them that are super old. We know how mud cracks form by a mud puddle drying up. There's no reason to assume that those ancient mud cracks didn't also form from mud drying up. If we find a reason to not believe that, that'd be one thing, but we really haven't found mud cracks form without mud drying up. Mountains and oceans, a bit more complicated, right, than mud cracks, but you can still go through this process, try to figure it out. At one point, the prevailing theory was catastrophism, i.e. something short but violent happened to cause things like mountains and oceans to form. a high magnitude event, essentially, such as, well, as I said, a gigantic cataclysmic event. That's the only way you can make a mountain, because how else would you do it, right? But as we'll get into, we go to mountain formation. We do have ways to build mountains. Mountains are being built nowadays. The Himalayan mountain range is continuing to rise. How is it rising? Slow tectonic processes. So if slow tectonic processes can create mountains today, why couldn't slow tectonic processes create mountains in the past? Again, when we get to that chapter, I'll go more in depth. We're still kind of in the introductory portion of geology here. Going through the checkpoints again. Feel free to pause and take a look. Try and answer the questions to the best of your ability. And I believe that is, yeah, that's basically the chapter. So take everything you thought about here. Feel free to write questions and comments down below. In the following chapters, we're going to dive deeper into actual geology. This is just a precursor because it's important to understand what geologic time is and how it relates to the world. Because I'm going to be talking about things that take tens, hundreds of millions of years. And I'm not even going to care about the fact that I said 100 million years. Because that is the process that you have to think at. This is not, I mean, the only thing that's comparable is astronomy. And we will get to astronomy at the end of the chapter, right? At the end of the book, sorry. So yes, that's why we cover this. I skipped over some things that are perhaps confusing, but if I plant the seed now, and we talked about mountain building formations, or we talked about metamorphic rocks, talk about igneous rocks, hopefully this stuff will click a bit better. So thanks for watching. It's been a pleasure. Send me an email if you got any questions. Leave any comments below if you want. Take care.